As we introduced in the previous lecture, from now on we consider linear codes either as image of an FQ linear map phi, which can be defined in terms of their generator matrix, and often we will denote them by their parameters, or we will define them as the kernel of a projection map, which is defined in terms of parity-check matrix. So that means often we will be interested in the first encoding part instead of decoding in algebraic coding theory. And for this insight, we may consider k-dimensional, or instead of a finite field of size q to the k, or k-dimensional vector space over k, we may consider the vector space which contains polynomials of degree at most k minus 1, and by evaluating each polynomial at given n distinct point alpha 1 up to alpha n, alpha i's from FQ, and they are distinct, we can construct linear codes with respect to this evaluation, because obviously phi is an FQ linear. But for the Solomon codes, we will represent these elements from the finite fields in terms of the primitive element of the multiplicative group of the finite field FQ. So in other words, if you consider the non-zero elements from FQ, its size obviously q minus 1. So actually, this also tells us to be able to evaluate a polynomial given n distinct points. For the construction of the Solomon codes, we will suppose that the length of the code will be less than or equal to q. So the length will be short compared to the base field, compared to the size of the constant field FQ. And for the vector space consisting of polynomials of degree at most k minus 1, let me use the notation Lk for given k. And let me denote this FQ linear map by evaluation map from Lk to FQ to the n by evaluating the polynomials at the powers of the primitive elements of FQ. So here in this case, the length will be q minus 1. And obviously, evaluation map is FQ linear. And indeed, if we suppose that k is less than or equal to n, such a map is also one-to-one. And in order to see that, if we consider a polynomial which lies in the kernel of the evaluation map, so that means this is going to be polynomial whose evaluations at given beta i's, while I runs through from 1 to n. This can be only zero polynomial, because otherwise if f is non-zero polynomial, so since it is an element of fk, it's going to be degree at most k minus 1. But if it is in the kernel, that means it has n distinct roots, because the distinct powers of the primitive element are also distinct. But since k is less than, or I mean the dimension can be at most the length of the code, k minus 1 is strictly less than n, so this is not possible. This gives us contradiction. It means this is one-to-one. And thanks to this injection, indeed we can view the image of this evaluation map as a linear code of length n and of dimension k. And with this particular choice, so that means if we choose our n distinct points, or if we represent our n distinct points in terms of the primitive elements of fq, and if we consider L of k as a polynomial space with respect to this evaluation map, we can introduce what is called a Ritz-Solomon code. And often we write RS code in short. And second question, okay, we have a construction of this important family, of course. The second question is that what is its minimum distance? At least do we have an upper bound or the lower bound? And to understand its minimum distance, since it's a linear code, it's enough to check how a weight of a code word in C, so it has to be by the construction evaluation of some function f, some polynomial f, and to count the non-zero coordinates of a code word, we will count the number of the zero coordinates and when we remove them from the m coordinates, we will get a minimum, at least the weight of a code word. See? So here note that the degree of f is at most can be at most k minus 1. So that means the size of this set indeed can be, so that means since the degree of f can be at most k minus 1, it can have at most k minus 1 roots. So that means the size of this set can be at most k minus 1. This shows us weight of any code word is at least m minus k minus 1. On the other hand, by the signature bound, we also know that its minimum distance is less than or equal to n minus k plus 1. And this shows us the minimum distance of the Solomon code is n minus k plus 1. And indeed, it shows us Solomon codes are MDS codes. So when we view them as image of NFQ linear map, so if you want to describe them in terms of their generator matrix, it will be enough to consider again the definition of evaluation map, and indeed the image of the basis of the domain LK, and indeed their evaluations at given distinct points beta to the I gives us linearly independent code words in C, and indeed for this case we will come across a structural generator matrix or in general if you consider a matrix whose rows are determined by the powers of n distinct elements from alpha 1 to alpha n, we can represent the generator matrix of Solomon codes in this way. So that means we can view the encoding of a message of length k as multiplication by this generator matrix G. And we will get the same definition of the Solomon code. Indeed, we can also define Solomon code in terms of their generator, in terms of their parity-check matrices, or in some sense, in terms of some parity-check equations. And for this purpose, for a code word C, by using FQ linear isomorphism between n-dimensional vector space and the quotient ring FQX modulo x to the n minus 1, we can view this a vector of length n is a polynomial of degree at most n minus 1 with check equations. So that means it will be determined by the polynomials who has roots at beta, beta square, and beta to the n minus k. Or we can write these conditions as a system of linear equations. Or if we represent this system of linear equations as a matrix multiplication, this is going to be n minus k times n matrix multiply by column vector of length n is going to be 0. And we can indeed easily check that this H is the parity-check matrix of Reed-Solomon codes with the generator matrix J we considered here. Sorry.